All right, this is Women Who Code Python. Welcome everyone. Our mission, we are a global nonprofit dedicated to inspire women to excel in technology careers. Excel is what sets us apart from other organizations because we want to work on gender diversity in tech. We want to concentrate on professional women engineers like you who are already in tech or who are trying to get in tech with a variety of backgrounds. We want to give you the tools, resources, and network to get and stay in the industry longer and excel to top leadership positions to meet your career goals. Our goals are empower women with skills needed for professional achievement, educate companies to better promote, retain, and hire talented women, build a global community where networking and mentorship is valued, develop role models, and support this generation of engineers. So this is our code of conduct. We are an inclusive community, so anyone who supports our mission and vision is welcome. We do have this code of conduct that you can check it out as well in womenwhocode.com/code of conduct. We have different tracks. We have front end, mobile, blockchain, cloud, Python, which is us, and we have data science. We want to thank our sponsors. Without them, we couldn't be here tonight. So we appreciate them as well. So let's get into where we came from today. So this is NLP contextual word embeddings, what's new and how to use them. This is a talk by Shreya. A little bit about her. She's a data scientist at GoDaddy in California. She builds deep learning models for language data. Previously, she completed her master's degree in statistics from the University of Illinois at Urbana-Champaign, where she worked on a hierarchical Bayesian model for geospatial data. She has been in coding in Python for the last 5 years, and she has also spoken at the GeoPython 2019. She's very passionate about spreading tech education at the grassroots level and believes that access to technology should be a basic right. So I'm going to pass it out to her.
All right. Hello, everyone. My name is Shreya. I'm going to be sharing my screen with you in just a second. All right. So today we're going to be talking about contextual word embeddings. And first, let me give a little bit background about myself. Okay. So as Linyana introduced, I have been working at GoDaddy, mostly on unstructured language data, and I work on the deep learning side. Previous to that, I was working on geo-based models on Bayesian modeling. So if you ever worked on that and are interested on working in it, feel free to feel free to ping me on LinkedIn, GitHub. I will be sending out those links at the end of the presentation. I also have my GitHub link if you for this repository for the tutorials that we'll be covering today. And you can go through them at your own pace. And you can, I've given all the instructions to install the libraries, to how to run the notebooks. And there's a bit of introduction on how to run those code. So let's get started with contextual word embeddings. The outline of the talk is going to be in 3 sections. So first, we're going to be talking about what word embeddings are. We're going to be looking at Word2Vec, Glove, Elmo. After this, we'll be taking a short break. And if you have any questions, if you have any doubts, concerns about any of the slides, feel free to post them in the chat or the Q&A. And basically, I'll be scanning them and answering them at the end of each section. The next section is going to be about transformer attention, what basic pre-processing techniques we have in the recent state-of-the-art models. And in the last section, we're going to be talking about Bert. So Bert is this new state-of-the-art model for language representations, and basically how do you make your model understand language on a much more deeper level. We will be looking at some other transformer-based models as well. And throughout the, I'm sorry, throughout the presentation, I will be basically fidgeting in and out. Don't worry, it's just that I'm very fidgety and I like moving here and there. It's not that I have to go to the toilet or something. Um, all right, so let's get started with the first section. So we're going to be talking about vocabulary here. As you know that the basic, oh wait, let's see. So audio is still going in and out, about 3 to 5. Okay. Is it the same for everyone? Is audio and video okay? Can everyone see my screen?
Yeah, I want to make sure because I can hear you fine. Yeah.
Oh,
like
okay.
it might be just one person because
Yeah,
I hear you
yeah.
fine too.
Might be some
Now
internet connection problem.
Yeah, it might be their connection. Okay.
Okay, great. Good to know. Everything's working good. All right. I'll get back here. Okay, we're going to be talking about vocabulary now. So you know that the basic piece that your language is made of is a word, right? You start from a very small vocabulary when you're a kid. You have very few limited words. And then as you grow up, you get more data, you talk to more people, you collect more knowledge, and you have more vocabulary. Basically, this is how models build as well. If you're building a very simple model with limited vocabulary, it's going to understand very small part of your language. Let's say you feed your model a book or a corpus of very few articles. Let's say you have a list of 10 Wikipedia articles that you're feeding to your model. It's only going to understand very small pieces, very small sentences, right? Because it's not a lot of data. That is why with the growth of vocabulary, we have newer models coming up, we have newer representations. And to discuss this, we'll go back at the very basics. So one of the most basic ways that the word embeddings are constructed or the words are represented is through a one-hot vector. But you need to understand why we even need these word vectors. Let's say you will have a word or a sentence, and basically you want to represent that in a computer, or you have to feed that to a machine learning model. Now the thing is that most of these machine learning models, they only understand numbers. They do not understand your characters, your words, spaces, punctuations. They have no idea about what these mean. So in order to make your model understand what each word is, you need to construct your vectors in such a way such that there is a mapping of each word to a vector. And how we do this is in a very variable way. So from the very basics when we started, we had this problem of doing one-hot encodings. What is one-hot encodings? It's something very simple, and I'm pretty sure if you worked with language at one point or other, you've used this. So let's say in our vocabulary, we have this man, woman, boy, girl, prince, and we assign each of these words an integer, as is shown on the left. Basically, you give all of these vectors a size that is equivalent to your vocabulary. So if you have 9 words, you have a vector of length 9. And you give 1 at the position for which the index is true for that word. So if man is 1, it gets 1 at that place, and the rest everything is 0. If it's a girl, it's at index 4, you give 1 here, and rest everything is 0. This is called one-hot encoding. Now, as you can see, it's not very space efficient, right? Let's say you have a vocabulary size of 32,000, 20,000. I mean, if you know, so the most average human being has a vocabulary about 20,000 to 40,000, depending on if you're a teenager or if you're an adult. So, and it really varies, right? You know different words, every language has different words. But basically, if you have such large vocabulary, how do you represent each of those words as a separate vector? If you go on representing them as this one hot vector, it's going to take too much of space. Each word is going to be of about 32,000 length, and that is not efficient at all. So that is the motivation behind creating word embeddings. So with word embeddings, we want to have a very dense structure instead of the sparse, very low on information vector that we had with one hot vectors. And we want to have those vectors in such a way such that when you actually project them in an n-dimensional space, you want to be able to see those relations very clearly. So by relations, I mean stuff like this. So let's say you are projecting the word man, the word woman in a three-dimensional space, and you want to be able to make this relation that the way the man and woman are related should be equivalent to the way your king and queen are related. In fact, this is one of the most basic examples that you will see in natural language processing. You will see that you want to get relations like man plus woman minus king should be equal to queen. What that means is that basically whatever relations you're getting here would be the same relations you want to see over here. And you could make these relations with every word you see. You could see them in tenses, you can see them in different forms of the word, you could see them in prepositions, you can see them in countries, capitals, and basically you want to be able to capture this, you want to be able to capture the meaning behind the words. And they're not just words, you want to be able to visualize them in such a way. And the more important thing about this is that you don't have to do this by hand. You don't have to actually assign each word integer and then you have to make this whole vector of 32,000, right? These are dense vectors. By dense, I mean each of them, like if it's a 50-dimensional vector, each of that 50-dimensional vector, each element is a floating point. So you don't have zeros just like the previous one. Having these means that you have much more information in a single vector. And this saves us a lot of computational power as well. So in word embeddings, we see a lot of applications, right? Let's say you want to do language modeling. Language modeling is this very basic task where you have a sentence and you want to calculate the probability of that sentence, right? And how do you do that? It's very simple. It's a basic chain rule. So you start with the first word. You calculate the probability of this word being the first. Then you see the second word given the first word. Then you calculate the probability of the third word given the first two words, and so on and so forth until you reach the end. So basically, this is a very simple way to calculate the probability of a sentence. And what this helps us is understanding how sentences are formed. You can generate sentences, you can talk to a chatbot, you can create apps for answering questions. I mean, recently with all the COVID-19 stuff, there have been a lot of applications where people have been building, let's see. Okay. Oh, yes, I can share the sheets. Or do you mean the...
I think she means the presentation. So.
Oh, okay. I will share the
Share
presentation, but that will be after the talk. So, and I will also share the notebooks and everything in one GitHub repo. So, okay, continuing to where we were. So we have all of these language-based models, right? And we want to be able to give our machine learning model this context of what a sentence means, how sentences are constructed, and so on. Oh yeah, I was talking about COVID-19, sorry. So COVID-19, all of this stuff came up with the doctors wanting to build apps in order to answer questions that people have. So let's say you suspect that you've been having symptoms for the last few days and you want to be able to talk to someone, but because of the shortage of all of these health professionals, there's been a lot of load on hospitals, on clinic centers, and you want to be able to build an app that answers to the basic questions, right? So there have been challenges on Kaggle and Microsoft and Google. They have all been releasing all of these data sets that you can use. And it's also used in the word embeddings are also used in sentiment analysis. So let's say you have these comments on the Amazon platform, where you see that if there's a product, people can actually post reviews and they can see which ones are positive, which ones are negative, right? So if you read the first review over here, You can see that it has 1 star. And you can see words like not originals. You can see I paid this for what I thought would be original. So clearly the user is not happy. We know that. And the second one, if you see, they have 5 stars. And you see words like these are great for playing Uno, vibrant, larger than ordinary playing cards, seem sturdy enough. So you see all of these keywords that make you understand that this is a positive review. And basically, embeddings help us do exactly that. Each of those word embeddings makes us help the model understand what a positive thing is and what a negative thing is. All right, so we come to the dense vector part. Now that we've done with what word embeddings are, Word2Vec was actually introduced by Google in 2013, and this is actually a very simple neural network architecture. Now, for the rest of this presentation, I'm going to be assuming you know a little bit about neural networks, about what layers are, what softmax is. But if you have any questions, if you are not clear with something, please do post it in the chat and I can answer them at the end of the section. So yes, so let's look at Word2Vec. Now, Word2Vec was this paper in which they had 2 different forms of models. One was skipgram. So the architecture you see on the screen is of skipgram architecture. Let's say you give your model a single one-hot encoded vector. So you have, so if you remember, we need to have as many elements in that vector as our vocabulary size. So if you have around 10,000 of a vocabulary, you need to have the input vector of this size. And this is only one word, right? Because you have one at only one place and the rest, everything is 0, just like the one hot vector. And you give it to your hidden layer, neural neurons. And basically this could be of any dimension, but in the paper, they had 300 dimensional representations. And then you give it to another softmax layer. And the softmax layer, what it does is it gives you the probability of every word in the vocabulary that you can have. That can probably you can see in the context of this word. And now, what do I mean by context? Context would just mean if you can see it around a certain word. So let's say you have a sentence called shallow neural network architecture. Now you give the network a word, let's say neural, and you want to be able to predict the probability that you see shallow or network or architecture around that word. This is the first kind of model that they built. The second one was continuous bag of words. The continuous bag of words was the complete opposite. Instead of giving the model just one word, they would give it the whole context. Now, by context, they define a context window. Like you could have 100 of words as a context, right? But in the paper, what they did was they chose a context window of 10, which means they looked at 10 words before, they looked at 10 words after, and gave that as input to the neural network. And they wanted to predict the current word using just those 20 words. Now, this was the continuous bag of words approach. And basically, they saw with these unsupervised learning-based models, they could construct vectors, dense vectors that actually could capture the meanings of different words. And this is how the paper was released. Okay, and now we're going to be looking at certain other another tutorial just to make things clear. Okay, cool. Let's see. Okay, no more questions as of now. Okay, so this is the tutorial that is actually available on the TensorFlow website. But just for the case of simplicity, I'm going to be going through this demo one by one so that we know what we're working with. So if you've ever gone on TensorFlow website, all of the tutorials are based on the latest version of TensorFlow. So make sure you install the latest version here. And let's see, here is your embedding layer. The first thing that you need to create for your network. I'm going to be working with TensorFlow datasets. So TensorFlow datasets is this module where you can load pre-processed dataset, and it's easier if you go through this as a beginner. So let's go through this. So the first thing that you do is create an embedding layer. This is the number of neurons that you want in your embedding layer. And basically, this is the number of dimensions that you want your hidden representations to be in. So like if you want your representations to be 16 dimensional, 20 dimensional, 30 dimensional, this is what you're going to be looking at. And this, this is the vocabulary size. So if you're looking to construct, so if you remember the architecture we saw, if you're looking to construct embeddings, you want to be able to map your integers to those embeddings. And this is what this layer exactly does. Now, if you want to get your embeddings of a certain integer or of a certain word, and you know the index of that word, you can just type in here and it'll give you the embedding layers. Here we load the IMDb movie reviews data set. What we're doing is we're just splitting it into test and train, and we're going to be learning embeddings from train, and then we're going to compute the accuracy on test and see how our model is performing. It's very simple. Now here is a glimpse at our vocabulary. Now, if you see you have all of these underscores at the end, don't worry, these are just your spaces, sort of. So the way the data is pre-processed is that it consists of subwords. And subwords are different than normal words of the dictionary that you see. Subwords are mixture, or there's something in between characters and words. And for the sake of simplicity right now, you can just assume this to be a space. Now we're going to be talking about padding. So let's say you have all of these huge data sets, but you're going to be batching them because that is how neural networks work, right? You need to batch them. But let's say you're having, you don't have exact batch size multiples of data, right? So you need to pad them as well. All right, now that the basic pre-processing and loading and everything is over, we come to the main part. We come to the model. We're going to be using the Keras API. Since TensorFlow 2.0 came out, we've been working with Keras instead of the conventional TensorFlow routine that had, that had graphs and then no eager execution. Since 2.0 has come out, we've seen this huge new change in the way you can construct models. So you can now actually debug very easily. Earlier, TensorFlow used to be a little difficult for beginners, but if you're thinking about getting into language processing, you can now go on with TensorFlow or PyTorch, either way. All right, here we define an optimizer. We define a binary cross entropy loss because we're going to be training on sentiment analysis, which means you're classifying labels of 0 and 1. And we're going to be looking at accuracy here. We train it for 10 epochs. We see that the accuracy is 96 point something, and the validation accuracy is 85. So you see that there is a major difference between training and validation. You can actually diagnose why this is happening, if it's overfitting, and so on. You can plot your diagnostic plots. You can look at the way your loss is decreasing. So over here, you see that your validation loss is decreasing to an extent, but then it starts increasing, whereas your training loss continuously decreases monotonically. That is the case that you will usually see in almost all machine learning models. Similarly for accuracy. I'm going a little bit fast, but feel free to go through this at your own pace, and feel free to shoot a message if anytime you see a problem or a question. Now, we've created these word embeddings, but we want to be able to visualize them, right? If you have your own data set, you create these new embeddings, the first thing that you want to do, you want to see if those embeddings make sense to you, right? And TensorFlow actually gives us a nice tool to do that. Now here, I saved my vectors and I saved my meta file, which is just the list of words that I have. And I loaded them onto this TensorFlow projector. So TensorFlow projector, what it does is, even though your dimensions of your embeddings might be significantly higher. You could have a 300 dimensional thing, you could have a three-dimensional embedding, you could have a 10-dimensional embedding. What it does is, once you load the data here, it will use a dimensionality reduction technique to actually load it into a 3D space, and you can visualize how your words are together, how your semantics, if they're being captured in your corpus or not. So like here I search for the word wonderful, and you can easily see that the words around it are favorite, stunning, excellent, exceptional, necessary, surprise, magnificent. So you see that it is able to capture at least some sentiment about what these embeddings are. You can similarly, you can search for any other thing. You can use TSNE as your dimensionality reduction technique and figure out what those words mean. All right. Now let me get back to my presentation here. Okay, now that we're done with Word2Vec, I hope that was a good introduction. If you already worked on this might be repetitive for you, but hopefully we're getting into the much more difficult and interesting part right now. So after Word2Vec came out in 2014, the Stanford researchers published GLOVE. So GLOVE is another different algorithm to construct those embeddings, but they don't look at a neural network. How they do this is they basically calculate how many words occur together with each other, and that is called co-occurrence. So what they do is they make a pass through the whole corpus that you have, and with this, your corpus could be anything. It could be, again, a book, it could be tons of books, it could be Wikipedia articles, anything. And you basically go through each of them one by one, and you calculate your matrix. And your matrix is going to be your vocabulary size into your vocabulary size. And then you're going to see how many times each of those words appear in the context of another. Now, the way they actually want to encode this information is through probability ratio, right? They want to be able to see that what is the probability that some word appears in the context of some other word. And how they do this is like this. So this is the table that has been taken from the paper. And at the bottom of each slide, I've also given the source of each image, of each information that I'm getting. So after the presentation is over, you can go look through them, figure out if you find it interesting, you can go through it in more detail. Now, this is a very simple example of what is the probability that you have a solid given ice. What is the probability that you see this in your corpus? So the way to calculate this probability is very simple, right? This is elementary probability. So a probability of something of A given B is the number of times you see A and B together, and divided by the number of times you see the word B, right? So here also we calculate this using the same mechanism. And as you can see, because our corpus has so much of vocabulary, this probability is going to be extremely small, as you can see. Now it's in the order of 10 to the power minus 5, minus 4, which means that there is very less information. You could probably normalize it to make it seem on a better scale. But what the authors did was they wanted to see what is the probability of seeing a word in terms of two other words. So let's say you are doing, you have this column, and you want to be able to see what is the probability of solid given ice given that, divided by solid given steam. So if you have something like 8.9, it means that a numerator is very high, right? And it means that the probability that solid given ice, which means that you see solid in the context of ice, is much higher than you see solid in the context of steam. Now that is what it means. And similarly, for something that is really small, you could make the opposite connection, that you see gas in the context of steam much more than you see gas in the context of ice. And using this context is how they create embeddings. And if you see something that is very close to 1, which means both of them have very low chance of being seen with either of them. This was how GLOVE was made, and it was a significant change because it does not use any neural networks at all. To actually give you a glimpse of how GLOVE embeddings are, is that, okay, so this was actually GLOVE of 50 dimensional. So these are all 50 different floating points. this is for king, this is for man, this is for woman. And basically what we're doing is we're trying to encode information in each of these elements, right? They've been colored from red to blue, which means that anytime you see a similar color along this, they have similar values. The range is very different, but for the purpose of this, you don't have to worry about the range. You just have to see which of the vectors are similar to each other. Now, if you see king and man and woman, you probably notice one thing, that this dimension has blue, that this dimension has red, and that probably man and woman have something in common here, right? This is one way to actually visualize. Now, you could do this with tons of examples, right? But to be able to make a much more sophisticated or a much more exhaustive hypothesis, you want to be looking at a huge data set, just like the TensorFlow projector we have, and be looking at various words to see if it makes sense to you. But you could probably hypothesize just by looking at these three examples that this probably means they are people, or this probably means that they have been, these are some terms that are related to household, or because they've been seen so much together, or that these two are seen much more commonly than this word. Now, instead of these three, let us look at a lot of other words, right? Now you see one thing, which is this red is common throughout all of these vectors, right? Now we don't know. So that is the thing about language, right? And you can visualize and you can make hypotheses, but you cannot know for sure if this is what you're seeing. But it's actually a very good way to build intuition of which vectors are similar and which vectors are not. So even if people work with neural networks, one of the things that they complain most about is that it's not interpretable, you don't know what's happening. But here's the thing, even if you're working with images or if you're working with language, visualization is one of the most basic ways you can actually figure out what's happening. If you look at your gradients, how they backpropagate through each of these layers, you can figure that out. In the later coming slides, we'll be looking at attention. So attention, again, is a mathematical phenomenon in which you can figure out which words are paying attention to which other words in the sentence. So if you have to work with neural networks, definitely go for some visualization techniques that actually help you in understanding what the model is doing. It's not that it's not interpretable, it's just that you have to find new ways to interpret the model. And as you can see here, like woman, girl, boy, man, they're all very similar in some way, right? And you can see queen here, which is not similar to any of them. But you can see that these all of them are very high blue, and this is not, right? Which could probably mean that all of them are living, or all of them are persons, people, whereas this is not. You could go on making hypotheses. It's just a very fun activity. All right. Now, before we break for our first section, the last thing we're going to be covering is Elmo. Now, Elmo was actually released 4 years after GloVe. That does not mean there were no other innovations in the field of contextual word embeddings. But Elmo was this new feature, new algorithm, because it meant that representation of a single word is no longer constant. By that, what I mean is, so let's say you're given a word in a particular sentence, like, let's go to the bank today to withdraw some cash, right? Now, you could probably go through Word2Vec, you could go through GloVe. The only thing is that because all of them have been trained on a single corpus, they have single word embeddings for each of those words. But what Elmo did to change this was that Elmo built contextual word embeddings, which meant your word embeddings are no longer constant for a particular sentence. I meant for a particular context. So that means if you are giving it one context, you will have one set of embeddings for a word. If you're giving it another set of sentence, so let's say I say now that let's go to the river bank to have breakfast. Now this bank refers to a different word, which means we want to be able to get those different embeddings, right? We don't want our model to understand that the same way as a financial bank. And this is the problem that Elmo captures. Now, whenever we talk about language, we always talk in terms of ambiguity, right? We have a lot of ambiguity. We have a lot of words in which even if you're a native speaker or if you're a non-native speaker, you get confused about all of these ways that English language is used. We get confused about synonyms, homonyms, homophones, right? Now, to be able to make your model understand that, you need to be very specific about the context that you see it in. How do we make sure that we understand different meanings of different words? It's because we have been shown two different sets and we've been told that they're different. And one of the most important features of Elmo was that it actually builds on character level, which means that you do not have to work with words, which means that any out of the vocabulary word, anytime you get a rare word, it's not going to be out of the vocabulary, but it's going to be built on character level. And it's a bidirectional model, which means it looks at the sequences from right to left as well as from left to right. And the way these representations are constructed is that it's a neural network model, but it's basically built on all of the layers representations. So if you have two layers, let's say, you have hidden representations at one level, hidden representations at another level. And basically what Elmo will do is it'll learn a linear combination of both of these representations. Yes, and now we come to the tutorial. Okay. All right. Okay. Now I'm going to be talking about Elmo here. So for the purpose of this tutorial, we've been using Allen NLP. So this was released by Allen AI, which is why the authors have this open source library that you can use easily. Again, it's a different framework. Okay. And it's a different framework. And basically, it's built on top of PyTorch. But if you want to be able to do things very coherently, you should do read documentation. I've posted the link here. And they have examples of what their data sets are, how you read a data set, how do you perform classification with it, and so on. So let's build a very simple model here. So right now, what we're doing is we are defining our data sets, we are defining what each sentence is, and if given a file, we will just read from a file and then convert it to tokens, and those tokens are going to be converted to index. If you see this hash, 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 do not worry, this is just another subword pre-processing technique. This is the LSTM model we're going to be building. It's very simple. You stack layers on top of each other. You have a linear layer at the end, which is the same as a dense layer. And you make a forward pass. If you have labels, which means that you're training, you have an accuracy metric. If you do not have labels, it means it's just inference or prediction, and you go on by just producing your output. Now here you define how much size of the embeddings you want, what is the hidden dimensional, which means what is the number of neurons you want in that layer, hidden layer. And basically, if you have a GPU available, you define your optimizer and then you start training. It will give you the best epoch, what is the accuracy, what is the best validation accuracy, and so on. Now, sentence predictor is your predictor model that these guys have. And basically, you can convert your whatever sentence you're giving it to input the way the model understands, which is tokenizing and then indexing it. And you can predict the tags over here. Again, this is a very basic example, But let's say you do not have to build your own embeddings every time, right? Let's say you just want a place where you want to be able to figure out what is the Elmo embedding of this sentence, of this word in a sentence, and so on. So these guys, you can do this in probably just less than 2-3 lines of code. So they have an Elmo model. You just give it an options and a weight file, which is found on their website. And basically you have, let's say you want to give this sentence and you want to be able to get the embeddings. It's as simple as just feeding the model those IDs and you get the embeddings here. Now, let's say you want to calculate the cosine similarity between two sentences. What I mean by cosine similarity is often you want to be able to predict how similar two sentences are, right? You want to be able to see how one question is similar to another. Like Quora released this data set, which was detecting duplicate questions, right? You could calculate the similarity of two questions here by just feeding them the embeddings and then calculating the cosine similarity, set a threshold, train a model, and there you go, you have your model ready. And this is, you could probably experiment more with whatever they have in their open source library. But the only thing that I want to convey here is that you don't have to build your model from scratch each time. Make sure you're going for their pre-trained embeddings, and you have all of their code to actually look at. You can mess around with the hyperparameters. You don't really have to create your own model unless it's absolutely necessary. All right. Now, this is probably the last slide for this section, but how do you use word embeddings? Now, we've seen that you can create them on your own. You can use, you can just create a learning, an embedding layer, or you can train it with the whole model task. So like you don't have to train the whole corpus first, and then you have to feed them to the model. No, you can just give them the embedding layer and it will learn directly with the supervised task you have. You can use pre-trained embeddings just like the Elmo last model we saw. You could actually do this, and this is the pretty much the most used technique in machine learning research. You could actually seed or start the model training with the pre-trained embeddings, and then you could train it jointly with the model. And why this is the most chosen one is because it's the most fastest one. Your model converges faster if you use it with something that is pre-trained, because the pre-trained ones have already been verified as working really well. All right, and now we come to the questions. Let me see if there are any questions.
If you go to the Q&A, there are 2 questions.
Yeah. Okay, let me see. Okay. Can you elaborate on the neural network? How exactly? Oh, so Elmo actually uses LSTM. I did not put the architecture diagram on this on the slides, but the way the Elmo is constructed is that it has LSTM layers, and LSTM layers are nothing but long short-term memory, which is a unit that is used in RNN layers. So RNN layers capture the history of your sequence, which is why it's also the reason that it is that it's sort of capturing the history, which is long term. So if you're having a sequence, it will look at it from left to right. It's bidirectional, so it will also look at it from right to left. And that is the reason that Elmo has actually proven to be really good, right? It's a bidirectional language model that you build. And how exactly is the final embedding created? Okay, so what Elmo authors did was that these guys had a stack of LSTM layers. And basically what they, for your task, if you want to learn the embeddings, is that they use a linear combination of all of these hidden representations that are stacked on top of each other. And let's say you give them the input, you calculate the hidden representation that each layer, and you have to and then the final embeddings is just a linear combination of all of them. That's it. Okay, can I explain skip grams? Yes, and I will do that. Just the last question. Do you mind giving an intuitive overview of Bert? Oh yeah, I'm going to be going to Bert later on. That is, I think, in the third part of the section. So because we're going to be progressively moving towards much more complex models till we reach the state of the art, which is Bert. Okay, let me actually share my screen, go back to the presentation, and explain scriptgram again. All right, so skipgram is, I hope you meant skipgram in the context of word2vec. If you mean skipgram in the context of language modeling, it might be a little different. But the way word2vec is built is, this is the skipgram architecture. So you give it just one word, and basically you're trying to predict what all words can be found in the context of this word. So if you define a context window of 10, you say what is the probability that I see each of the words in my vocabulary in plus or minus 10 of this word. That's it. That is what the whole skipgram model is. And basically the authors of this paper at Google, they found out that if you use this to train your model, if you use this representation, and you can also use the continuous bag of words, but whatever representations you get over here at the hidden layer, they actually speak a lot about semantics. I hope that answered the question. But now let's go back to our major thing, which is pre-processing. So in pre-processing, what we do is, this was actually taken from data compression. So what we have is this, let's say you start at the character level for all of your words, and you want to be able to be having vocabulary in such a way such that out of vocabulary words do not cause a problem. So often in often in your corpuses, you will see that some words occur a lot, whereas some words do not occur a lot. And usually what we do is we just set a threshold on frequency, like if this word is seen a lot, it's taken in the corpus, it's taken in your vocabulary, otherwise it's not, right? Because you cannot have all of the words, as that will exceed the computation that you could probably have control of. So we start with the character level and we build things on top of each other. So let's say you have all of this corpus, you divide all of them into characters, and then you see which of the character sequences occurs a lot, and then you build words on top of that. Word piece is built in a similar way, that instead of using the number of times you see each character sequence, it's built on the statistical concept of likelihood. And likelihood is like, what is the probability that you will see this occurrence of character sequence in the model, or in the corpus, sorry. All right, now we come to sequence models. Now these are very interesting models. If you worked on language translation, you know about them already, right? Sequence models were built based on this structure. It's very simple. You have this input sequence and you want to be able to convert that to an output sequence. So like here, you would have something in one language, and then you're trying to translate it to another language. You would give it all of the corpus over here in the input would be monolingual over here. And then you would have the same corpus exactly translated. It's actually called a parallel data. And you would have the same thing translated to output. This is how all sequence-to-sequence models are built. And this is the reason we come to transformer, because transformer is also trained to actually be used for machine translation. So this was actually published in 2017 by Vaswani and others, and it's a really huge big breakthrough in the field of natural language processing. And that is because of the results it posted, and not just because of what this paper did, but because of the research that followed this paper. So there have been so many variations of transformers. There have been so many studies on just to how to make transformer faster, because it has a lot of complexity. And you have a lot of architectures that are messing around with it. You have a lot of papers that are working on how to increase the speed, how to make it work on a smaller, let's say, smaller computer. And so the way this is built is that we have a transformer made of encoders and decoders again. But instead of just having one encoder, one decoder, we have 6 of them. And each of those encoders has this. Each of them has 2 layers, attention layer and feed-forward neural network layer. And the decoder has attention layer, some other attention layer, and feed-forward. The reason I'm just calling it as very vague attention layer is because I'm going to be explaining that in the coming slides. But for now, just think of them as a decoder. It has 3 different things it has to pass through. And you have one encoder stacked on top of each other. So if you see here, this is just one encoder, but imagine 6 of them stacked on top of each other and 6 of the decoders stacked on top of each other. That is how the transformer is built. All right, now coming to the attention. Now, attention is this mathematical concept that actually helps you figure out ambiguity. So it helps you understand what each word in the sentence can be related to other words in the sentence. So if you have this very simple phrase that you see, the animal did not cross the road the street because it was too tired. Now, if I do not give you any of this, the animal did not cross the street and because it was too tired, right? So if I do not give you any of the previous context, you would have no idea what it is referring to. But because you have this previous historical data to use, you can probably figure out, right, that it is referring to the animal. Now, this is what attention did. Attention was made, it's a mathematical formula that actually helps you focus. So it places weights on all of the words in the sentence, and it helps you understand which word it is focusing on. And the way the authors did this was through embeddings and creating 3 vectors, which is queries, keys, and values. So what the author did was, the first thing is that they have embedding, which is randomly initialized in the beginning, as always. Okay, let's see. Okay, just about the recording, no questions till now. Okay. Yeah, so the first layer over here is embedding. Then you create 3 vectors using 3 weight matrices, which is WQ, WK, WV. And so Q is created using this matrix. Keys are created using this matrix. The values are created using this matrix. I know it seems very high level, very abstract right now, but just bear with me for 1 second and I'll explain how it all comes together. So imagine you have these 3 vectors, queries, keys, and values. Now, the reason you want them is because you want to be able to query each of the words in the sentence, and you want to be able to figure out if that word is actually related to the word that I'm probing. So if I'm at W1, I will use Q1, and then I'll multiply it, and I'll take a dot product of Q1, K2, Q1, K3, Q1, K4. So think of it like you are shaking hands with each of those words, and basically you want to see which handshake is the most firm, right? And the authors also found out that if they put a softmax layer on top of this dot product and they multiply it by the value vectors, they get much more better results. But I hope the intuition over here is clear. So what happens each time you're decoding is that, let's say you have your input over here. This is the input before you send that to the encoder. You have the embeddings. You have the time signal, which signifies that this position is number 1, this position is number 2, this position is number 3. The reason we do that is because we can run things in parallel. Another thing that the transformer is actually very popular for is that you can run things in parallel by just adding this time signal. If you have this time signal, you can run all of these computations. So like if you have an encoder here, this will go through one way, this will go through another way, this will go through the third way. But you don't have to make them go sequentially. These can go run in parallel. So which fastens up your computation time very much, right? And each of them goes through the layers that we talked about. It goes through an attention layer, so which means each of them will query the other vectors keys. So like if you have K1, Q1 over here, it will query K2, it will query K3, and basically it will form the attention layer. Then it goes to a feed-forward neural network, which is just a dense layer. And once you have those hidden representations at the end of the stack of those 6 encoders, you go here. You come to the decoder. Now remember, the decoder had this another second layer in the middle, right? Which was called the encoder-decoder attention. And which is why it had these different vectors, different matrices in the middle, because you're actually inputting those keys and values and figuring out the encoder attention. Because the decoder has, if you think of it, like you are giving the hidden representations to the decoder, right? And it has to figure out what those mean. So which is why you need keys and values for, especially for just those encoder hidden representations. And it's very simple here. So if you go through it one by one, the decoder will use the previous output to prevent the current input. To predict the current output. So now student will come as input here, and then it will predict whatever the next word is, which is end of sentence. So at the decoder side, it goes through one by one the output that is predicted. So you have am, that goes as input. Then it predicts the next word, which comes as input again, and then so on till you reach the end of sentence. Now, I know that was a lot of information overload of what attention is if you've never heard of it before, but attention is not new. Attention was actually introduced in 2014. And why transformer was more famous is because it uses this multi-headed attention. It's different in the way, remember we had keys, we had values, we had this query vector. The authors also found out that if they would have 8 attention heads, which means that you would not focus on just, you would not calculate just one piece of attention, you would calculate 8 of them, which means you have different matrices, you have different matrices for each of those attention heads. So imagine that computation into 8, which is why it's also very computationally expensive. But the thing is that most of these computations can be run in parallel. So if you have multiprocessing, if you have multiple GPUs, this sure helps a lot. And so just to think of multi-headed attention more intuitively, you have, so let's say you're again working on it, this word. So imagine now you have different attentions that you can focus on different things. So like if you have 2 of them, you could probably focus on one attention head could be on the animal, and the other attention head could be on too tired. And why is that? Is that because you're answering questions about that. So the first question that the orange head is answering is that who is it, right? Who does it refer to? But the second question that your attention head over here is answering was that why did it not cross the street, right? So you have so many complex sentences that we see that are built of phrases that are so grammatically complex that maybe one attention wasn't enough to capture the whole semantics of it. That is why they needed 8 of them just to be able to tell that this word or this sentence means something else entirely. All right, with that, we reach the second part. Don't worry, it's not a lot of parts are left, just that Bert, and we'll be going through the Bert tutorial. But let me see if there are any questions. Oh yes, I will give an overview of Bert. Do not worry. The next section is all about that. I do not see any other questions right now, but okay, so let's go on. All right, and now we come to the last part of the talk, which is Bert. So Bert is this, again, at the base, it's a transformer, but the way it's trained and the way it's used is very different. And that, I mean, that is the whole speciality of Bert, is that they use unsupervised pre-training and then they train on supervised tasks. By what do I mean by unsupervised training? Is that they have this whole corpus and they build the data in such a way that you don't need to have separate labels for any task. And in the fine tuning stage, what they do is they have certain specific tasks that are very well defined in the whole natural language processing community. And you have certain predefined benchmarks that you need to beat. They tested their model and pre-training and all of the techniques on all of these basically squad, MNLI, named entity recognition texts, data sets, and they found that their model actually performs and beats state of the art. Now, just to show you what Bert is actually famous for, right? Now, Bert is this, it takes a whole, I think it's a books corpus that they have and a list of Wikipedia, a set of Wikipedia articles that they're using for training, pre-training. So what they do is in the pre-training stage, that is the first stage, that is before you have any of the supervised learning tasks. In the pre-training stage, you have that they construct two tasks. One is the masked language model, and the other is the next sentence prediction. So amongst their corpus, they create a data set in which you have a sentence and a sentence that follows immediately after it. And they construct also pairs where they have a sentence, but the next sentence is not actually in the corpus. So it's just any random sentence. So you see you have this whole 50%, 50% sort of data where a sentence is either the next one or it's not, and they train it on this task. The other task is the masked language model. The masked language model works something like this. So they have, it's a bidirectional model, which means that you are looking at your data left to right as well as right to left. And that's because the authors thought that if you have a word, it should never be looked in isolation by just looking at the left-hand side, right? You need to be looking at the right-hand side as well to be able to figure out what it exactly means. And what they do is they take their whole corpus and they choose 50% of the tokens at random. And what they do is with an 80% probability, they will replace it by this token mask. With a 10% probability, they will replace it by any random token. And with a 10% probability, they will let it remain the original token. And then they will feed it to their to the transformer based model that they have. It's at its base is just the transformer that we talked about. And they will evaluate by predicting the masked words. And they will compute their accuracy. They will evaluate, they will test the accuracy based on all of these masked words, the 15% of them that were done. Let me go back actually to the fine tuning stage. So the fine tuning stage is where the model is predicting stuff on data sets where you have supervised data, where you have labels. So let's say this could be in sentence pairing. If you're looking at if one sentence is a paraphrase of another, if you're looking at question answering, so it could be like, is this line an answer of the question that is asked? So this is often a thing you see in reading comprehensions. Or if you want to classify in sentiment analysis or something, that could also be done with Bert. So how is the Bert pre-training actually work? So you could possibly give it a pair of sentences, or you could give it a single sentence. So if you give it a pair of sentences, you have to be able to give it a separator so that the model knows. And that is actually given by this token here. They're using a 30,000 vocabulary, which if you see is not much at all, because like I said, the average vocabulary that a human knows is about 20 to 40K, which is exactly what they want to be giving the model. Often when we start working, we start with very limited. We start with 10K, 20K, 30K, unless we see a really high increase in the language understanding of our model, we really don't want to be using very high vocabulary. Okay, now before we go to the other models, let's actually go and look at the tutorial that we have. Okay. Now we come to the tutorial part. So this is based on transformers. Now, if you go to the GitHub, I'm actually going to be posting this in the chat. Let's see. Okay. Cool. So this is the repository right now. So if you go to the notebooks, you will find all the notebooks here. And I've given instructions as to how you can install stuff for each of those notebooks. You might see that your virtual environment might be clashing in some of them because of the way the libraries are constructed. It is always the case that the basic thing that you want to be doing with deep learning is to actually set up your virtual environment starting from scratch. Because if you have your virtual environment set up, you have half of the stuff done. And so we used the transformers and tokenizers, which is from Hugging Face. You have all of these transformer-based models that are available. You just load them from the pre-trained models they have. And basically, you can encode in a very simple way. You just encode it like this using a tokenizer. Here we use the Bert tokenizer that the authors had. You feed it to the model, you get the embeddings. Now, if you see over here, you tokenized and you got a vector of length 1, 2, 3, 4, 5, 6. And yet, if you do the shape of the last hidden layer, which is the embedding that we're going to be using, it's of 8. And that's because the way Bert is constructed, it pads a special token in the beginning and at the end, which is CLS and separator. So CLS is just the beginning of the sentence, and separator is the one that separates two sentences. So it's only because of the way the Bert is constructed that you need these two tokens. So you can get the hidden layers, and these are your embeddings that you're going to be using. So again, if you talk about how two sentences are similar, you can probably do a very simple check. Is how you can actually, because it's of 768. 768 is the hidden dimension of the representations, and basically you could just form the average across this dimension, across axis 1. And you could form these embeddings for each of the sentences. So remember, these are the embeddings you get for each word. And if you want to find sentences, you could probably do that. So I tried doing that, but I'm just sharing what I found. So I tried doing that just by stacking or squeezing it along one dimension, but that did not work. As you can see, I got a very low similarity score on this. The young kids are playing outside, a group of kids is playing in a yard. We know that this pair of sentences is actually pretty similar, but the model or the way that we've computed this is not representative of the similarity that I want to see. Similarly, the dogs are wrestling and hugging. There is no dog wrestling and hugging. So these are completely opposite sentences, and they should have embeddings that have no similarity at all. And yet, the cosine similarity that I'm getting exceeds the one that I found above. And this is why I wanted to introduce this Bert as a service. So Bert as a service is this another library that was released. And basically, you can get Bert embeddings directly. You just have to start the server and the client. To actually download and install, I've given instructions on GitHub, but basically you need TensorFlow less than 2.0. So if you're using the same virtual environment as other notebooks, this notebook might, so your client server here might not work. So make sure you actually install a whole new virtual environment having TensorFlow less than 2.0. I've explained that in the GitHub link. So once you do that, you just want to encode them, you get their sentence representations, and they have various pooling techniques by which you can get sentence representations. And once you do that, you can just compute cosine similarity, and that actually makes much more sense here as compared to the one that we were getting above. So this is something that I've used in the past and I found really useful. So if you want to be, if you're working on some Kaggle data set, some other challenges, and you want to compute semantic similarity, this is the thing you look at. Coming to now to actually using transformers to train your own model. I know we're nearing the time, but this will only take, I think, about 2 or 3 more minutes. So just bear with me. And here you load the TF Bert for sequence classification. You just, so in the demo here, we're going to be using the Microsoft paraphrase corpus, which means you're predicting if one sentence is a paraphrase of another or not. And once you load the whole data sets, this is pre-processed and it's available in TensorFlow data sets. Once you load all the data sets, it's very simple. You define your optimizer, your loss function, your model, and you just fit it for these many epochs. But remember, this is very computationally expensive. So unless you have hours to spare on your laptop and you don't have to do any major computation work, you can leave it running, run this on your local. Otherwise, I would suggest using Google Colab, or if you have access to a GPU, if you have access to, AWS and both Google Cloud, they give out free credits. If you have access to those, definitely try this out there. For me, I was just for the purpose of the demo, running it on my local host, and I stopped it in the middle because I only wanted to get very basic results. So over here, you have the model. One good thing about these models is you can save it in TensorFlow and then load it in PyTorch just like that. So if you're working with 2 frameworks simultaneously, which is not recommended, by the way, if you're working on the same problem, but if you are and you want to be able to use it interchangeably, you can do that. Here we use predictions, and basically this is prediction of whether one sentence is a paraphrase of another or not. And you can get a 0 or 1 prediction over here. Talking about multilingual Bert, it's as simple as using the Bert base. So you just load this model, it will download, and you can use it the same way we did the previous one. Here I tokenize a Spanish query, and here I tokenize a Hindi query. You see all of these hashes. Again, these are because of the way vocabulary is constructed using word piece. So do not worry if you think that this does not make sense to you. It's just the way that the Bert tokenizer works. And you get the last hidden layer. You basically have these as your representations. So you have representations in 104 languages in the model that was released from Bert Multilingual. You can also use the masked LM to predict. So like here, what I did was I gave it a piece of text, and I wanted this word to predict. So I gave it the target as happens, and I replaced this happens word with a mask. And I asked my model if you could just tokenize the whole text and then feed it to the model, and then I want to predict the actual one. So here, the predicted token is occurs. So if you see the original sentence, the embedding only happens in the bottommost encoder. You could actually use this. The embedding only occurs in the bottommost encoder. So all of the other outputs that were given also make sense to me, right? So the embedding only is in the bottommost encoder. The embedding only exists, appears, falls, happens, in fact, the 6th choice. So you see that the model is actually able to figure out what word that could be. And that is a very good thing. That is how you actually see that the semantics of the whole sentence are represented correctly. Okay. And now I'm almost done. I know we're stretching a little bit out of time, so I'm going to be doing this very quickly. But because the transformer really led to this whole new field of staging where you could pre-train and then you could test on supervised tasks, we see a lot new models that came up. We see Transformer XL, where you could possibly get longer dependencies. So if you have sentences where you want to capture long dependencies amongst them, so if you want to capture long historical contexts, you could do that via Transformer XL. Facebook released this cross-lingual model, which means that you would basically have one pre-trained data set, one data set that you would use for pre-training, and basically you could predict stuff in another language using just the monolingual one. And this is also very good to look at. And remember, all of these models are at your hand. You can use them in to the transformers library that you have. It's just a matter of as small as 5 lines of code probably, that you just have to load the model, load the tokenizer, get the embeddings, and just go from there. All right, I hope that during this session, I was able to give you a good glimpse of what word embeddings are, what word embeddings are popular, how do you create them, what is a transformer, how do you get Bert representations, and how do these models actually work. I hope you were able to get the intuition behind what attention is, because that is very important. Mostly all sequence-to-sequence models, all of the new models that are coming in NLP right now use some or the other form of attention. And mainly, I hope that you were able to realize that you do not have to reinvent the wheel. You do not have to always think about training a new model. You can fine tune, you can use pre-trained ones. In fact, that is the way to start. You don't start building from scratch, right? You see whatever's there in the literature, you try to seed your model using that, and then you begin fine tuning your model according to the task you have. These are some of the references, and these were some of the blogs that I found useful. Definitely check out this one, the last one. It actually gives you a very simplistic view of what's happening mathematically behind the transformer. And I'm also going to be taking questions right now. And let me see if there are any questions. Okay, so the first one is, with masked language model, why only replaced 80% of the 15% with mask? What is the purpose of the remaining 10% random? And what is the purpose of replacing 10% with original? That is actually an excellent question, and something that we all have when we read about the masked language model. So the reason they wanted to replace it with mask is because they didn't want to include any bias in the training data. That is what the authors decided. And it's not clear as to why it was only 80% or why only 15%. It's actually that the authors experimented with a lot of different values of percentage of which they could mask. And they wanted to, they realized that getting that percentage of data of masking only 15% and 80% of those 15% masks, which actually worked. They have done a lot of ablation studies about that as well. Okay, also, can you cover GPT-2? I don't think we have enough time to cover GPT-2 right now, but I can actually add something to my presentation or to my GitHub link after this. Is the recording available? I think there will be recording available. It was posted in the chat.
It will be available. I just share the playlist where we upload them, but it will be in a couple days. It wouldn't be tonight.
Okay. All right. So it's not going to be here for a couple of days. Sorry, it's going to be here in a couple of days. So there will be recording available. How do we? Oh, yeah, this is a good question. How do we decide which pre-trained model to use? So one of the most basic constraints that you have is the computation power at your hand. Remember, you have versions of transformer. You have versions of transformer that work on a very very basic chip as well. So you have all of these light models, right? So if you're working with limited computational power, start with light models. So like me, what I do is I usually look at the base model of even if I have to work with Bert, you have these Bert base, Bert large, multilingual, KIST. So if you're working with multilingual data, you will decide you need the Bert multilingual, but always start with the most basic one. And the reason why that is because if your model is proving to be really good, like it has a good accuracy, does not overfit, is able to understand the semantics behind your language, do not go to the higher model unless absolutely necessary. Like we start with, so if you're starting with transformer, definitely go for the easiest, most base transformer. Do not go looking at embeddings of size 1024, look at 768, look at smaller dimensions instead of actually looking at very high ones. Because often what we also do is we have very less data available, and we think that by using a much larger model, maybe this less data will be compensated for, but that is not the case. It usually just overfits on that huge model. The other way to decide on which pre-trained model to use is to actually go through the literature. Like most of us, what we do is we go through the literature, figure out that this task that we're working on is very similar to the task that was used by the authors, and we start with the exact same hyperparameters that the authors used. This saves us a lot of our dev time, because often we don't have time to check exhaustively. Like we don't have time to make this hyperparameter grid and check everything, right? So that helps as well. Someone asked about embeddings and which embeddings to use. So again, static embeddings you can use. It's just that they're very simple to make. You can create them yourselves. You could use static embeddings in cases where you're not very worried about homophones, homonyms, and stuff like this. But if you really want to be able to capture contextual embeddings, which means that in each sentence you have a different embedding of a word, and if it's the same word, you can have different embeddings in different sentences. Definitely go for the newer ones, like we have the Bert one. And yes, I will be sharing the slide deck. I will be uploading it to the GitHub repo. I did not do it till now because I was working on that. But yeah, I will do it as soon as this talk ends. Cool, I think I answered all of the questions.
Thank you very much for the presentation. That was very insightful, and people will have the information. Everyone is saying thank you. And if you have any questions as well, you can ask in the Slack channel we have. Thank you very much, everyone.